Continuation of our explanation on topological manifold, we are going to look at what we mean by locally Euclidean. What we actually mean is that I want as an example. Now, every point on a manifold can be viewed locally as a point in an n-dimensional Euclidean plane. What we mean is that there exists a what we call homeomorphism. Homeomorphism, okay, between points in M. Let me call my, where M is M. By M I mean the manifold. Okay, and Rn, an n-dimensional Euclidean plane. Okay, consider an example of torus. Torus is an example of topological manifold. Okay, now if you now define a map, supposing this looks like what we call a car tire. Okay, isn't it? A car tire. Okay, this looks like it's tire of your car, the torus. Okay, now it's an example of manifold. But supposing you want to fetch a portion of it, now you build a map between this and dimensional manifold, so that every point here is mapped onto a point on this. So that means you are now saying that there exists a map F. Okay, so that means you are now constructing a map F from points xi, of course, in the manifold, and they are mapped to R2. Okay, topological manifold. So by the time these points are mapped like that, they will appear in R2 as a flat surface. Meanwhile, these points, which I have said, are actually on a torus, but when you map them, they will appear on a. So that's what we mean, that there is a map from M to R2, and this map F is homeomorphic. Okay, so that's what we mean by locally Euclidean, and the physicists will tell you that this represents what they call degree of freedom. That means as long as you remain close enough to the R2 surface, there is always a projection from the n-dimensional manifold to n-dimensional Euclidean plane. And this actually says a lot, because it is our understanding, our comprehension of the complex structures of the manifold by reducing them to flat surfaces of the Euclidean plane. So I will come to the next presentation.